Hello, this video is about the Nobel Prize in Chemistry for the year 1914, awarded to Theodore Richards for his accurate determinations of the atomic weight of a large number of chemical elements. You see him at work in 1905. And here you see some of an illustration coming from one of his articles, a graph with atomic weights of several well-known elements, as you can see. Okay, then why did he got the Nobel Prize? The Nobel Prize in Chemistry in 1914 was awarded to Theodore Richards in recognition of his accurate determinations of the atomic weights of a large number of elements, chemical elements. This is coming from the official Nobel Prize site, as you can see. Here's the link. Here's also some biographical information, also coming from the Nobel Prize site. About half of Richards' original work was concerned with atomic weights, starting in 1886, with work on oxygen and copper. He quickly developed a new technique for the determinations of Halley-Deur ratios and did much towards improving the methods of weighing. He invented the nephelometer and demonstrated the insidious effect of occluded moisture in gases and solids. By 1912, he had redetermined with the highest accuracy the atomic weight of over 30 important elements, and in later years he was to play his part by his work on determining the determination of the atomic weight of isotopes in the modern concept of the atom. During his initial work, he was guided by G.P. Cook. Richards also studied atomic and molecular volume, and he formulated a hypothesis of compressible atoms. He carried out a series of measurements of compressibilities of many elements and compounds in support of his theory, developing, applying and testing new methods and techniques. He introduced the use of transition temperatures of pure hydrated salt as fixed points in the standardization of thermometers, and the fundamentals of adiabatic calorimetry were developed under his guidance. His researches are recorded in some 300 technical papers, published mainly in the Proceedings of the American Academy of Arts and Science, the Journal of the American Chemical Society, and the publications of the Carnegie Institution of Washington. This is a summary. Of course, in reality it's a bit longer. If you want to read the complete biographical information on this man, follow the link. Here you see, by the way, carbon, as you can see, with atomic number 12, and carbon is used as the, how do you call it? The standardized unit. Yes, the atomic mass of carbon is 12 units, and all other atomic masses of the other elements are expressed in this unit. Then the award ceremony speech by Professor H.G. Söderblom. Of the work accomplished by Professor Richards in determining the atomic weights of so many elements, it has been maintained that it represents a gigantic task. Ever since the year 1887, his labors have gone on interruptedly right up to the date of awarding him the Nobel Prize. The result of his labor was been that no less than 30 atomic weights have been redetermined with a degree of accuracy undoubted never before attained, and by the employment, moreover, of methods by comparison with those in earlier use, mark a very appreciable advance. It should be pointed out that the determinations in questions embrace all those elements, like oxygen, silver, chlorine, bromine, iodine, potassium, sodium, nitrogen, and sulfur, whose atomic weights are customarily termed fundamental on account of their forming the basis for the determination and calculation of the atomic weights of all the other elements. From a purely quantitative point of view alone, the work involved in these determinations is very considerable indeed. Apart from Berzelius, the great pioneer, no one investigator who has contributed anything like so much as Richard. That becomes very obvious if we compare the case of stars of 12 atomic weights, including, it is true, in their number all the fundamental elements. Stas's atomic weight determinations had the reputation of being the well-nigh unassailable precision. At all events, the elements that he set out about determining in the period immediately preceding the accomplishment, in conjunction with Cook, of his first scientific investigations, were all of those that were not included in the series of investigations carried out by Stas, like copper, barium, strontium, zinc, magnesium, nickel, cobalt, iron, uranium, calcium, and cesium. For by far the majority of these elements he was able to show that early determinations were subject to considerable sources of error, which the method adopted and practiced by himself enabled him to avoid or render nugatory. Richards had, it is true, as early as 1894 fancied that he obtained values and proportions diverging considerably from those arrived at by Stas, but it was not until the year 1904 that he felt himself justified in seriously and publicly calling in question the correctness of a number of Stas's determinations. They were followed by a redetermination of almost all of other atomic weights arrived at by Stas, with the exception of carbon, and these two, in the majority of cases, were found to require exchanging for more exact values. Most of Richard's atomic weight determinations are so exact that any variation there may be is measured in thousands. Their correctness has been controlled in several ways, both by Richard's own counter-experiments and by the work of other investigations. The scientific world has moreover accomplished them by ever-growing need of recognition. The atomic weights established by Richard in his school were accepted to the fullest extent by the International Commission, which has been charged with the task of critically reviewing the recent advances made in stoichiometry and of drawing up year by year an atomic weight table for general use based upon the results of that review. Not only have Richard's atomic weights been directly embodied in this table, they have also been adopted as a basis for the recalculation of some atomic weights of an earlier date. He has not rested content with the demonstration incorrectness of all earlier determinations, but to detect in detail the actual causes of the mistakes and to point out expedients for obviating them for the future. Stas in his time developed to a high degree of perfection the mechanical physical manipulations that form a feature of the technical process of atomic weight determinations. He succeeded, thanks partly to that and partly to his making use of very large quantities, several hundred grams of material, in reducing the errors in calculation practically speaking to nil. Richard demonstrated, however, that the chemical operations give rise as a rule to more sources of error than do the purely mechanical processes and the reading of weights recorded, and made it clear that the value of the latter incurred the risk of becoming illusory because of the uncertainties in the readings. By operating with very large quantities in weights, Stas unconsciously laid himself open to one of the most serious of the sources of error referred to, that of carrying out his precipitation reactions in much too concentrated solutions, the consequence of which was that the undissociated salt present in the solution were condensed on the phases separated off in solid form, thereby impurifying them in a much higher degree than he had reason to expect. Realizing that the errors in question are diminished in the same proportion as the number of free ions present in the solution is increased, Richards has succeeded in exempting himself from this error by employing smaller quantities from 5 to 20 grams of the substance being experimented with, and by working in very dilute and consequently highly dissociated solutions. Among the other sources of error that have been pointed out by Richards, exercising as much greater influence than investigators have been inclined to attribute to them, we may mention the following in particular. 1. The presence of hygroscopic moisture in almost all the substances. 2. A remarkable degree of solubility in apparently insoluble compounds, and the attribute possessed by precipitates of remaining susceptible in the fluid exceedingly finely diffuse form. 3. The inclusion and occlusion of solvents in crystal, so-termed fixed solutions. 4. The occlusion of gases in metal oxides and other solid bodies. 5. Impurities resulting from the vessels employed in various operations. In order to remove as far as possible the cause of error 1, above Richards had constructed special apparatus, on the one hand for the expulsion of every trace of moisture from substances, and on the other for the exact weighing of those substances in an absolutely dry atmosphere, free from every risk of the absorption of water. Bottling apparatus. Richards, by adopting and adapting an earlier key, has constructed his well-known nephelometer, which by the use of reflected light allows of a reliable quantitative assessment being made of opalizing quantities of substance so small that they could be determined gravimetrically only with the utmost difficulty, if indeed at all. Richards has combined it to a large extent with centrifugation. With the aid of the phase rule, Richards has carried out a detailed investigation of the factors that determine the retention or disappearance of the occluded glasses in metal oxides. Finally, by exchanging, in numerous cases, vessels and apparatus of glass for others made of quartz, he had protected himself from the most serious effect of the disadvantageous circumstances referred under to Era 5 above. Well, as you can see, this is a summary of the press release. It was not a real award ceremony speech because there was no award ceremony in 1914 and during, of course, due to the war. So the Nobel Prize lecture given by Richards was only given, I think, in 1919, 5 years later. Well, this is it for the moment. We see now here see some earlier work by earlier investigators. You see only about 20 or so atomic numbers were known in that time. At that time is 1840. And here you see an apparatus, what's called a mass spectrometer, which is used to determine the mass. Okay, next week we will go into the Nobel Prize speech given by Williams not in 1914, as I said, I believe it was in 1919, which was, of course, delayed during the war. That was happened with more of those speeches, of course, and the same is true for World War II. For now, thank you for watching, and maybe until another time.